getting in shape with minimal energy, a variational principle for protohalos. In analytical models of structure formation, protohalos are routinely assumed to be peaks of the smoothed initial density field, with the smoothing filter being spherically symmetric. This works reasonably well for identifying a protohalo's center of mass, but not its shape. To provide a more realistic description of protohalo boundaries, one must go beyond the spherical picture. We suggest that this can be done by looking for regions of fixed volume, but arbitrary shape, that minimize the enclosed energy. Such regions are surrounded by surfaces over which the gravitational potential is constant. We show that these equipotential surfaces provide an excellent description of protohalo shapes, orientations, and associated torques. Next article. ALMA lensing clusters survey deep 12 mm number counts and infrared luminosity functions at C18. We present a statistical study of 180 dust continuum sources identified in 33 massive cluster fields by the ALMA lensing cluster survey over a total of 133 arc-2 areas, homogeneously observed at 1.2 mm. ALX enables us to detect extremely faint sources by lensing magnification, including near-infrared dark objects showing no counterparts in existing at Hubble Space Telescope and its Spitzer images. The dust continuum sources belong to a blind sample with SN 5.0 or a secondary sample with SN equal to 4.0, 5.0 screened by priors. With the blind sample, we securely derive 1.2 mm number counts down to 7 UG and find that the total integrated 1.2 mm flux is 20.78.56.5 GI-2, resolving 80% of the cosmic infrared background light. The resolved fraction varies by a factor of 0.61.1 due to the completeness correction depending on the spatial size of the emission. We also derive infrared luminosity functions at C equal to 0.67.5 with the 1V max method, finding the redshift evolution of our LFS characterized by positive luminosity and negative density evolution. The total cosmic star formation rate density at C greater than 4 is estimated to be 161.25-21% of the established measurements, which were almost exclusively based on active nerve surveys. Although our general understanding of the cosmic SFRD is unlikely to change beyond a factor of 2, these results add to the weight of evidence for an additional SFRD component contributed by the faint population, including near-dark objects. Next article. An archival search for type Ia supernova siblings. Next article. Evolution of the outflow in the water fountain source eras 18,043-2116. We present the spectral and spatial evolution of H2O masers associated with the water fountain source eras 18,043-2116 found in the observations with the Nobian 45 and telescope and the Australia telescope for path array. We have found new highest velocity components of the H2O masers, and the resulting velocity spread of 540 km/s1 breaks the speed record of fast jets outflows in this type of sources. The locations of those components have offsets from the axis joining the two major maser clusters, indicating the large opening angle of the outflow. The evolution of the maser cluster separation of 2.9 massa 1 and the compact CO emission source mapped with the Atacama large millimeter array suggest a very short time scale of the outflow. We also confirmed the increase in the flux density of the 22 GHz continuum source. The properties of the jet and the continuum sources and their possible evolution in the transition to the planetary nebula phase are further discussed. Next article. Evidence for bottom light initial mass function in massive star clusters. We have determined stellar mass functions of 120 Milky Way globular clusters and massive LMC-SMC star clusters based on a comparison of archival Hubble Space Telescope photometry with a large grid of direct and body simulations. We find a strong correlation of the global mass function slopes of star clusters with both their internal relaxation times as well as their lifetimes. Once dynamical effects are being accounted for, the mass functions of most star clusters are compatible with an initial mass function described by a broken power law distribution Nm alpha with break masses at 0.4 solar mass and 1.0 solar mass, and mass function slopes of alpha low equal to 0.3 for stars with masses less than 0.4 solar mass, alpha high equal to 2.30 for stars with m greater than 1.0 solar mass, and alpha equal to 1.65 for intermediate mass stars. Alternatively, a log normal mass function with a characteristic mass log equal to 0.36 and with sigma equal to 0.28 for low-mass stars, and a power law mass function for stars with n greater than 1 solar mass also fits our data. We do not find a significant environmental dependency of the initial mass function with either cluster mass, density, global velocity, dispersion, or metallicity. Our results lead to a larger fraction of high-mass stars in globular clusters compared to canonical Krupa-Chabrier mass functions, increasing the efficiency of self-enrichment in clusters and helping to alleviate the mass budget problem of multiple stellar populations in globular clusters. By comparing our results with direct n-body simulations, we finally find that only simulations in which most black holes are ejected by natal birth kicks correctly reproduce the observed correlations. Next article. Multimass modeling of Milky Way globular clusters I implications on their stellar initial mass function above 1m. The distribution of stars and stellar remnants within globular clusters holds clues about their formation and long-term evolution, with important implications for their initial mass function and the formation of black hole mergers. In this work, we present best-fitting multimass models for 37 Milky Way globular clusters, which were inferred from various datasets, including proper motions from Gaia-Etter 3 and HSD, line-of-sight velocities from ground-based spectroscopy, and deep stellar mass functions from HST. We use metallicity-dependent stellar evolution recipes to obtain present-day mass functions of stars and remnants from the IMF. By dynamically probing the present-day mass function of all objects in a cluster, including the mass distribution of remnants, these models allow us to explore in detail the stellar mass functions of a large sample of Milky Way GCS. We show that, while the low-mass mass function slopes are strongly dependent on the dynamical age of the clusters, the high-mass slope is not, indicating that the mass function in this regime has generally been less affected by dynamical mass loss. Examination of this high-mass mass function slope suggests an IMF in this mass regime consistent with a Salpeter IMF is required to reproduce the observations. This high mass IMF is incompatible with a top-heavy IMF, as has been proposed recently. Finally, no significant correlation is found between the high mass IMF slope and cluster metallicity. Next article. Cosmic radioactivity and galactic chemical evolution. Radioactive isotopes add important ingredients to such modeling. The intrinsic clock of the radioactive decay process adds a new aspect of the modeling algorithms that leads to different constraints on the important unknowns of star formation activity and interstellar transports. Several prominent examples illustrate how modeling the abundances of radioactive isotopes and their evolution have resulted in new lessons. Among these are the galaxy-wide distribution of 26 Al and 60 K, the radioactive components of cosmic rays, the interpretations of terrestrial deposits of 60 Fe and 244 Pu, and the radioactive decay daughter isotopes that were found in meteorites and characterize the birth environment of our solar system. Next article. Via Machini 2.0 Full Sky Model Agnostic Search for Stellar Streams in Gaia Doctor 2. We present an update to Via Machini, an automated stellar stream finding algorithm based on the deep learning anomaly detector anode. Via Machini identifies stellar streams within Gaia using only angular positions, proper motions, and photometry, without reference to a model of the Milky Way potential for orbit integration or stellar distances. This new version, Via Machini 2.0, includes many improvements and refinements to nearly every step of the algorithm that altogether result in more robust and visually distinct stream candidates than our original formulation. In this work, we also provide a quantitative estimate of the false positive rate of Via Machini 2.0 by applying it to a simulated Gaia Mach catalog based on galaxies, a smooth model of the Milky Way that does not contain substructure or stellar streams. Finally, we perform the first full-sky search for stellar streams with Via Machini 2.0, identifying 102 streams at high significance within the Gaia Data Release 2, of which only 10 have been previously identified. While follow-up observations for further confirmation are required, taking into account the false positive rate presented in this work, we expect approximately 90 of these stream candidates to correspond to real stellar structures. Next article. The Pandas view of the Andromeda satellite system Roman IV global properties. We build a statistical framework to infer the global properties of the satellite system of the Andromeda Galaxy from the properties of individual dwarf galaxies located in the Pan-Andromeda Archaeological Survey at the previously determined completeness of the survey. Using forward modeling, we infer the slope of the luminosity function of the satellite system, the slope of its spatial density distribution, and the size-luminosity relation followed by the dwarf galaxies. We find that the slope of the luminosity function is beta equal to 1.50.1. Combined with the spatial density profile, it implies that, when accounting for survey incompleteness, M31 hosts 92-1926 dwarf galaxies with MV less than 5.5 and a sky projected distance from M31 between 30 and 300 kpc. We conclude that many faint or distant dwarf galaxies remain to be discovered around Andromeda, especially outside the Pandas footprint. Finally, we use our model to test if the higher number of satellites situated in the hemisphere facing the Milky Way could be explained simply by the detection limits of dwarf galaxy searches. We rule this out at greater than 99.9% confidence and conclude that this anisotropy is an intrinsic feature of the M31 satellite system. The statistical framework we present here is a powerful tool to robustly constrain the properties of a satellite system and compare those across hosts, especially considering the upcoming start of the Euclid or Rubin large photometric surveys that are expected to uncover a large number of dwarf galaxies in the local volume. Next article. Ionized gas kinematics and chemical abundances of low-mass star-forming galaxies at C3. We selected 35 low-mass SFGS less than 10.2 from deep spectroscopic surveys based on their CI 1908 emission. We used follow-up NIR observations to examine their rest optical emission lines and identify ionized outflow signatures through broad emission wings detected after Gaussian modeling of IAI 4959 5007 profiles. We characterized the galaxy's gas phase metallicity and carbon-to-oxygen abundance using a T-based method via the OEI 1666 OEI 5007 ratio and photoionization models. We find line ratios and rest frame use characteristic of high ionization conditions powered by massive stars. Our sample displays mean rest frame U 560 R, while 20% of them show U greater than 1000 R and U greater than 5 Ra, closely resembling those now seen in eight galaxies with JWST. We find low gas phase metallicities 12 log 7.4 to 8.5 and CO abundances from 21% 173% solar, with an apparent increasing trend with metallicity. From our OEI 4959 5007 profile modeling, we find that 65% of our sample shows an outflow component, which is shifted relative to the ionized gas systemic velocity, with mean Vmax 280 kms, which correlates with the sigmosphere. We find that the mass loading factor mu of our sample is typically lower than in more massive galaxies from literature but higher than in typical local dwarf galaxies. In the stellar mass range covered, we find that mu increases with sigmosphere, thus suggesting that for a given stellar mass, denser starbursts in low-mass galaxies produced stronger outflows. Thus, galaxies with higher mu tend to have lower metallicity, more intense bursts, and higher U. Our results complement the picture drawn by similar studies at lower redshift, suggesting that the removal of ionized gas in low-mass SFGS driven by stellar feedback is regulated by their stellar mass and by their sigmosphere. Next article. The gravito-electromagnetic approximation to the gravimagnetic dipole and its velocity rotation curve. In view of the observed flat rotation curves of spiral galaxies and motivated by the simple fact that within Newtonian gravity a stationary axisymmetric mass distribution or dark matter vortex of finite extent readily displays its somewhat flattened out velocity rotation curve up to distances comparable to the extent of such vortex transverse to the galaxy's disk. The possibility that such a flattening out of rotation curves may rather be a manifestation of some stationary axisymmetric space-time curvature of purely gravitational character, without the need of some dark matter particles, is considered in the case of the gravimagnetic dipole carrying opposite nut charges and in the tensionless limit of its Misner string as an exact vacuum solution to Einstein's equations. Aiming for a first assessment of the potential of such a suggestion easier than a full-fledged study of its geodesics, the situation is analyzed within the limits of weak field gravito-electromagnetism and non-relativistic dynamics, thereby leading indeed to interesting and encouraging results. Next article. Chemical models of adenine precursors cyanamide and carbodiamide in the interstellar medium. Cyanamide and its isomer, carbodiamide, may form adenine in the interstellar medium via a series of reactions. Therefore, they are considered key probiotic molecules in the study of the origin of life. We used the three-phase Nautilus chemical code, which includes the gas, the dust surface, and the icy mantle, to investigate the formation and destruction of cyanamide and carbodiamide. We added over 200 new chemical reactions of the two isomers and related species, and established a relatively complete network. We applied cold core, hot core, core, and shock models to simulate the different physical environments and found that the two isomers are mainly produced by the free radical reactions on grain surfaces. Our simulated results suggest that cyanamide and carbodiamide molecules come from surface chemistry at early evolutionary stages. Then they are released back to the gas phase, either by thermal process or shock-induced desorption. We speculate that it is an inefficient route to form a tautomer of adenine by starting from molecules cyanocetylene, cyanamide, and carbodiamide. Next article. Exploring the diversity and similarity of radially anisotropic Milky Way-like stellar halos, implications for dwarf galaxy searches. We investigate the properties of mergers that are comparable to the Gaia sausage Enceladus using cosmological hydrodynamical simulations of Milky Way-like galaxies. It was previously shown that these mergers occur over a wide range of times. We find that the merger progenitors span an order of magnitude in their peak stellar mass and include both rotation and pressure-supported galaxies. In a minority of cases, the GSE-like debris is comprised of stars from more than one merger progenitor. However, there is a close similarity in their chemodynamical property distributions, and the triaxial shapes of their debris are comparable around the solar radius, so it is not always possible to distinguish their debris. The merger progenitors host a variety of luminous satellites, but most of these do not follow the merger to low orbital energies. Between 0–1 of these satellites may survive to z equal to 0, but with no clear signatures of their past association. We show that the fraction of stars originating from GSE-like mergers is reduced for lower metallicities, and also within 5 kpc of the galactic center. Whilst these central regions are dominated by in situ stars, the ex situ fraction trends towards a 100% asymptote when considering the most metal-poor stars. Considering this, its near proximity, and its small volume on the sky, the galactic center lends itself as a prime environment in the search for the stars from the earliest galaxies, whilst avoiding contamination from GSE stars. Next article. Direct collapse black hole formation induced by internal radiation of host halos. We estimate the fraction of halos that host supermassive black holes forming through the direct collapse scenario by using cosmological n-body simulations combined with a semi-analytic model for galaxy evolution. While in most of earlier studies the occurrence of the DC is limited only in chemically pristine halos, we here suppose that the DC can occur also in halos with metallicity below a threshold value ZTH equal to 0.103Z, considering the super-competitive accretion pathway for DC black hole formation. In addition, we consider for the first time the effect of Lyman-Werner radiation from stars within host halos, i.e. internal radiation. We find that, with low threshold metallicities of ZTH less than or equal to 10⁴Z, the inclusion of internal radiation rather reduces the number density of DCBHS from 0.2 to 0.3 to 0.03–0.06 mpc3. This is because star formation is suppressed due to self-regulation, and the LW flux emitted by neighboring halos is reduced. Only when ZTH is as high as 10⁵Z, internal radiation enhances the number density of DCBHS from 0.4 to 1 mpc3, thereby decreasing the threshold halo mass above which at least one DCBH forms from 2/109 to 9/108 m. We also find that halos with M-halo 1011–1012 m can host more than one DCBH at Z equal to 0. This indicates that the DC scenario alone can explain the observed number of SMBH hosting galaxies. Next article. Nonparametric galaxy morphology from stellar and nebular emission with the Califa sample. We present a nonparametric morphology analysis of the stellar continuum and nebular emission lines for a sample of local galaxies. We explore the dependence of the various morphological parameters on wavelength and morphological type. Our goal is to quantify the difference in morphology between the stellar and nebular components. We derive the nonparametric morphological indicators of 364 galaxies from the Califa survey. To calculate those indicators, we apply the StatMorph package on the high-quality integral field spectroscopic data cubes, as well as to the most prominent nebular emission line maps, namely OEI lambda 5007, H alpha, and NAI lambda 6583. We show that the physical size of galaxies, M20 index, and concentration have a strong gradient from blue to red optical wavelengths. We find that the light distribution of the nebular emission is less concentrated than the stellar continuum. A comparison between the nonparametric indicators and the galaxy physical properties revealed a very strong correlation of the concentration with the specific star formation rate and morphological type. Furthermore, we explore how the galaxy inclination affects our results. We find that edge-on galaxies show a more rapid change in physical size and concentration with increasing wavelength due to the increase in optical free path. We conclude that the apparent morphology of galaxies originates from the pure stellar distribution, but the morphology of the ISM presents differences with respect to the morphology of the stellar component. Our analysis also highlights the importance of dust attenuation and galaxy inclination in the measurement of nonparametric morphological indicators, especially in the wavelength range 4000 to 5000 Ra.